working today on section 5.2. The title of section 5.2 is Verifying Identities. We're still using the same set of identities that we started with last time, which was these 4. We will do the next couple next class, which, yes, I know is after spring break. So we're extending this chapter over spring break for us. But we're going to continue to use these 4 things. Now, there's a bunch of hints and tips and tricks on this first page. It's all words. This is basically like a place for you to go when you get stuck. This is helpful from last class as well as this class. But today, we are verifying identities, which means we will be given an equation with an actual equal sign. We did not have equal signs last class. We're going to have them today. And what we're going to do is we're going to try to, let's highlight this one. Oh, I didn't put the highlighters out. Maybe circle, star, or underline. We're going to try to rewrite the more complicated side of the equation so that it is identical to the simpler side. We're not solving anything. We're treating it like the ones we did last class, but it's already told us the goal of what we should get at the end. So we're verifying the identity. I still abide by this information right here, number 3. It is helpful to express all trigonometric identities in the equation in terms of sines and cosines when you get stuck and see nothing else, because a lot of times things will cancel out. Tip number 4 is to make sure you recognize any of the shortcuts for factoring or algebraic operations, aka this is the difference of 2 squares. If you have the subtracting of 2 things that are perfect squares, you could immediately factor to x minus y, x plus y, or the first thing minus the second, first thing plus the second. The second one is called the sum of squares. The third one is called the the difference of squares. That's wrong. Those are not the right words. These are called perfect squares, both of these. This one just happens to be a plus. This one happens to be a minus. You square the first thing, double the combination, and square the second thing. Square the first thing, double the combination, square the second thing. These are the same. These are your sum and difference of cubes formulas. Again, these are just shortcuts for whenever you find the different algebraic identities that we're working with. 1 second. Okay, we are on bullet point 2. Bullet point 2 here underneath our factoring or algebraic operations. Basically, if we see that we're trying to add together 2 fractions, remember we can only add together 2 fractions to make one term when we have a least common denominator. So I have a little example here of that happening, and mine is color-coded to kind of make it make sense. I don't know if you want to color-code yours, but if we are trying to add 1 over sine plus 1 over cosine, they need to have a matching denominator, which means they should both have sine and cosine in the denominator. This first one is missing cosine, so I multiply cosines on top and bottom. This one is missing sine, so I multiply sine on top and bottom. And now they have the same denominator. I do realize they're in a different order, but multiplication can happen in any order. 3 times 5 is 15. 5 times 3 is still 15. Multiplication can happen in any order. Once they have a common denominator, all you have to do is add the numerator together. So that's 1 times cosine, which is cosine, plus 1 times sine, which is sine. So then we get this one. That's finding a common denominator. Tip number 5 is for the more challenging questions that when you are selecting a substitution or selecting like your process to use, keep in mind what the goal is. Keep in mind the side that you are not changing because it represents your goal. If we're trying to do this identity, we can see that somehow we have to get tangent related to cosine. One of the ways we can do this is by making cosine into secant, because secant and tangent have this Pythagorean identity. So you're looking for these connections between the different trig functions to try to see how you can change them and then get to your result. Last but not least, and we saw this last class, if you have a 1 plus a sine of x or 1 and then a non-squared term of sine or cosine, you probably want to multiply by the conjugate, because then we would get the difference of 2 squares, which can be replaced with our Pythagorean identity, and this is a typo. This should be squared right here, cosine squared of x. So we have a lot of tips and tricks. This is a good place to go when you're stuck and you can't get a hold of me next week when you're so graciously doing your homework over spring break. Sure. Okay, let's see an example. Again, this is really going to be like what we did last time, except that now we have an equal sign. You have to make a couple choices right here at the beginning. We are trying to rewrite one side to be equal to the other side. We're not solving anything. We're not doing inverse operations. We're not doing any of that. We are trying to get one side to match up with the other. So my recommendation is always to pick the more complicated side. In your opinion, which side is more complicated?
Right.
I agree. So everybody right now, highlight, or however you're indicating we're using one side. We are going to only work with this side, which means this is the goal. We want to rewrite the green one that I've highlighted to make it look like this. What are your spidey senses saying to maybe try first?
Cosecant.
What about it?
Change it to 1 over cosine.
Okay, we can do that. I started mine differently, but that totally works. So cosecant is 1 over sine of theta. By the way, I'm not going to do any of the color coding I did last time. I'm just going to use like black ink on this one. So it'll probably match the way you write things down. Okay, we've done that. What was the step we just did there? Reciprocal identity. Okay, so I still like seeing the reason for each step so I can follow your logic in case your logic is different than mine. All right, what else? What are our spidey senses saying we should maybe do?
Distribute.
I like it. Let's distribute, which means we're doing 1 over sine of theta times cosine and then times sine of theta. I'm going to show a lot of work. I know you may be able to do this in a quicker step, but we're doing 1 over sine of theta times cosine of theta plus 1 over sine of theta times sine of theta. So that is a distribute step. Notice how I'm only putting an equal sign on one side because I'm only working with one side. It's as if that cotangent of theta plus 1 has not changed. Don't touch it. We're doing nothing on the other side of the equal sign. But what do you see can happen here?
The 2 times.
They'll cancel out, yes?
Yeah.
So then I can say that this is going to be a cancel step. I'm also going to let us multiply this first one together so that we have it as one term. What's 1 times cosine? Cosine. So this is really just cosine of theta over sine of theta. And then those signs cancel out, so I have 1. We're really close because look at the way our pattern looks. We have something plus 1. Our goal was to have something plus 1.
Oh, yeah.
Can we change this into cotangent somehow? Yeah, isn't that its own quotient identity?
Yeah.
Cotangent of theta is equal to cosine over sine. And so boom, I have verified the identity. By only working with one side using the same rules from last time, I've gotten the left side and the right side to be equal and I'm done. This is why if you look at your homework page for today, there's no answer key because the problem is not done until you solve the problem and then you've gotten it right. If you can get one of your complicated sides to look like the non-complicated side, that's the answer. Make sense? Let's try another one just to see some like weird, maybe mathematical things we can do here. Remember, the first choice we're always making is which side is the most complicated.
Well, right.
I also agree with you. This is the most complicated. So we need to do something here to maybe make this better. Let's distribute first. Okay, I see that because we have something in front of a parenthesis. So we're going to distribute, which would mean I'd have tangent squared of x plus tangent squared of x times cotangent squared of x. So that was a distribute step. Feels like I made it worse, but I really did not. What can we do for all 3 of these, well, 2 pieces, but all 3 trig functions?
We'll combine the 2 cotangents. We make cotangent and cosine over sine.
Say that all one more time. I got lost. Sorry.
The cotangent?
Yes.
Can you make it sine, cosine over sine?
Okay, I see what you're saying. So you're saying cotangent can be changed to cosine squared of x over sine squared of x. Is that the only thing I can change here?
You could do the tangent.
Yeah, tangent has a quotient identity, right? So we're actually doing the quotient identity 3 times. Tangent of theta is sine squared of x over cosine squared of x, which means I'm going to have that in both places for tangent. That is the quotient identity 3 times. What are your spidey senses saying?
Cancel.
What cancels?
The 2 that are being multiplied.
Okay, question, because I get this question a lot. Is this the only thing that cancels, or can you cancel something here?
The square? No.
So remember, sines and cosines are acting like x's and y's. Would you be able to cancel out the squares if it said x squared over y squared? No. So that's the same rule when it comes to trig functions. And since we can only cancel when we're multiplying, we cannot cancel when we're adding. Unless it's positive and negative, the same thing. That's how you cancel. So if we are multiplying, that's how we cancel. This one, I have a cosine squared on top and bottom, and I have a sine squared on top and bottom. So what does that whole piece become? 1. So we're going to rewrite down this first quotient, my first term, because we didn't change anything about it. But then this whole back part becomes 1. That feels good. We feel like we did something. That was a cancel step. Ooh, yuck. So here's where my brain, when I did this yesterday, when I was preparing for this class, I looked back up at the goal and I was like, that's one term. I know there's 2 terms in the denominator, but there's not like a big plus sign adding 2 things together. So I somehow need to combine these 2 things together. What's the only way I can add and subtract fractions? If they have the common denominator. So right now the 1 is missing the denominator. Yes? Its current denominator is 1. So if I wanted it to have a denominator of cosine squared of x so that it matched the other one, what would I put on top of that fraction? Cosine squared of x. Right now it already says 1 over 1. What did I have to multiply it by? Cosine squared of theta of x, sorry. So I multiply the top by that. Once they have a common denominator, what do? Oh, let me write down my step actually. Common denominator. I write them as one fraction. I can actually combine like terms or just add the fractions. Say that again? What?
He said, can't you cancel?
Ooh, what? What can I cancel? Maybe cancel is the wrong word. What can that numerator change to? It can change to 1. Look at your list of Pythagorean identities. I see 2 things that are squared. That whole thing can change to 1 because cosine, sine squared plus cosine squared is equal to 1. So now I have 1 over cosine squared of x. This would have been the Pythagorean identity. Now, last class, we probably would have done the secant squared of x. Good morning. However, remember, our goal is not to get this down to 1 term. Our goal is to get it to match this. We are actually 1 step away. What is it? Look at your list of formulas. Maybe one we hand wrote in. What?
The cosine equals 1 minus cosine, 1 minus sine squared.
So cosine squared of x is equal to 1 minus sine squared of x. That's one of those variations on the Pythagorean identity that we hand wrote onto our table. Now that we have this as the answer where I've stopped working, do you see that it is the same as the goal that we started with? Yeah. So we aren't necessarily doing what we did last time because last class I probably would have had you change this from 1 over cosine squared to secant squared. But our goal this time is not to simplify it down to 1 term, but to change it to match this identity. We want to prove that they are actually equal to each other. So we work with one side with the rules I've given you to make it match. So it does require a little bit more creativity, maybe even than last class.
Are there still different ways where you can still have the same approach?
I believe that there are. I know there are a couple. If you change everything to sines and cosines first, that will inevitably make you do the problem a little bit differently. But eventually, if you follow math rules correctly and the identity rules correctly, you'll end up in the same spot. So yes, this is not the only way. As long as you don't make up your own math along the way, you use correct rules. Let's try one more. We might not finish this one before lunch, but we'll go ahead and get started. Which side do you guys think is the most complicated?
The right side.
I agree. Well, let's start with this one. So we're only touching this side. Our goal is to get this side rewritten so that it looks like this.
Okay.
To take this into account, do you notice that this is 2 separate pieces?
Yes.
So eventually I'm going to have to make 2 terms. First term, second term. So I'm eventually going to have to split this fraction apart to make two terms. In fact, I'm going to do that first. Because this is a monomial, no plus or minus in the denominator, it's all multiplied, I can split this fraction immediately into two pieces. Tangent of t over sine of t cosine of t minus cotangent of t over sine of t cosine of t. I highly recommend making your t's curly at the bottom so they don't look like plus signs. Do we see what I'm doing here?
Yes.
So because it's a monomial, I can split that fraction. Again, that's not quite the perfectly math word for what I'm doing, but it looks like you're splitting it. So we're going to write down the word split. Boof. And then there was like a whole lot happening.
Yeah.
Remember, when we get stuck, what should we change everything into terms of? Sines and cosines. So right now, we're going to use the quotient identity twice to make a mess, and then we'll clean it up. Because tangent can be sine of t over cosine of t. So that's what's going to be over sine of t cosine t. And then cotangent is cosine of t over sine of t. All of that's going to be over sine of t cosine t. That is your quotient identity times 2. Was that our lunch or our pre-lunch bell? Okay. Did I lose anybody? Did we follow the split?
Yeah.
I just took the same denominator and basically undid combining like terms. That's a split. From here, tangent changed to sine over cosine. That's it. Cotangent changed to cosine over sine. That's it. And then I keep the bottom. Yeah, the bottom did not change because all I did was the quotient identity to the numerator. Not quite yet. I mean, yes, but you might cancel it incorrectly if you don't keep change flip. We're going to keep change flip twice. Twice. And we're going to do that after lunch because I can tell we're already thinking about food.
Yeah.
Okay, after lunch we will keep change flip twice. Let's just refresh our brains how we got here because it's been a whole 30 minutes from lunch. So we recognized that the right side was more complicated than the left side, so we're going to start with the right side. I also noticed that our goal has two terms, so we went ahead and split this into two terms because it's a monomial in the denominator. And then we used the quotient identity twice to do tangent and cotangent. Now, right before lunch, we discussed how we were going to have to keep change flip these things so that we could see if something cancels. So let's go ahead and do that, which means we are going to keep the numerator and we're going to change the big divide to a multiply, and we're going to flip the denominator. The denominator is currently sine of t cosine t over 1. So when I flip it, it becomes 1 over sine of t cosine of t. I'm also going to keep change flip the other side. So this is cosine of t over sine of t multiplied by 1 over sine of t cosine t. Keep change flip. Now, the reason we wanted to do this is because potentially, and a lot of times when there's fractions and fractions, there are things that are going to cancel out. Is there something that cancels out in the first one?
Sines.
The sines. There is something that cancels out in the second one.
Cosines.
Cosine. So we have now, if we do this cancel step, we have 1 over cosine times cosine. Whoa, what's cosine times cosine? Cosine squared, there it is. We got there. Which means this side, if I have 1 over sine times sine, that's sine squared. Now again, don't lose the goal, because you might start to work backwards and start trying to make a common denominator and all this stuff. That's not what we're doing here. Our goal is to have two terms, check, we do, that have secant squared of t minus cosecant squared of t. Let's see if we're close. Is there some way 1 over cosine of t could become secant of t? What is 1 over cosine of t? It is secant. Okay, so reciprocal identity gets me there. What is 1 over sine? Cosecant. And so boom, we do the reciprocal identity times 2, and we now have it matching the goal. Our goal was to get secant squared of t minus cosecant squared of t. So we keep the goal in mind. Example number 3 may be hard to choose which side is more complicated until I point something out to you. If we look at example 4, what's your initial instinct on which side is more complicated? So remember when there's a monomial that you can like split it apart? That means it's actually simpler when the denominator is a monomial, which means for us that this is the more complicated side. So we are going to work this time with the left side. Now, because that left side has a binomial in the denominator, we cannot split this. So instead, we need to use some other ideas, maybe from our front page of this section, that give us something to do. Our last bullet point on the front page said that if you see 1 minus sine or 1 minus cosine or 1 plus, any of those things, we can multiply by its conjugate because it will be the difference of two squares and end up using a Pythagorean identity. So that's what we're going to do here. We're going to take cosine of x over 1 minus sine of x, and we are going to multiply the top and bottom by the conjugate of the denominator, 1 plus sine of x over 1 plus sine of x. So that step is multiplying by the conjugate. I'm going to show a lot of work in case we don't see the shortcuts. But let's go ahead and take that numerator. And in fact, I'm not going to distribute cosine of x because I've done this problem already. You may want to distribute the cosine of x from time to time, but maybe hold off because potentially something might cancel and we want to see the multiplication that's happening in the numerator. But when we multiply the denominator, it's the difference of two squares, or it's a FOIL question. 1 times 1 is 1, 1 times positive sine of x is sine of x, 1 times negative sine of x is negative sine of x, negative sine times positive sine is negative sine squared of x. This is a FOIL step. This is the difference of two squares. And I know it's a difference of two squares because what's going to happen in the middle? We have a positive sign and a negative sign. They cancel each other out. So we end up with cosine of x times 1 plus sine of x over 1 minus sine squared of x. When we're doing the multiplying by conjugate, it kind of leads us through these next couple steps. We always multiply by the conjugate. That means we have to FOIL. Something probably cancels. And then we do that to use the Pythagorean identity. Do you notice this is on your chart underneath Pythagorean identities? What is this equal to? Cosine squared of x. So we can change that entire denominator to cosine squared of x and leave the numerator exactly as we had it in the step before. So that is the Pythagorean identity. Now that I have a monomial in the denominator, things can start to cancel. What cancels top and bottom? Both of them?
Just one.
Just one. So it's like I get rid of the squared. So I have 1 plus sine of x over cosine of x.
Yay.
That was a Ooh, why'd you say yay?
That's it.
That's it. Correct. Remember, our goal is not to get it to a simplified single number like last class. This time we wanted it to match this problem. So the moment it matches the problem, we're done. So always keep the goal in mind. Otherwise, you'll start going around in circles solving things indefinitely. Keep the goal in mind. On example 5, which side do you think is most complicated?
The right.
I agree. When we have fractions involved, that's probably going to mean that is our more complicated side compared to no fractions. Some things I notice are that this becomes two terms. So at some point, we're going to have to split apart this fraction. Can I split it when the plus sign is in the denominator?
No.
No, you can only split when there's a monomial in the denominator. And I don't see anything like squared, so I know Pythagorean identities are not going to work. What did we do last time when the problem didn't have squares, but it had a 1 and a cosine or sine? What's the first step that we did? Yep, flip back. What does it say? What's the first step we did in the last problem?
The last problem?
Mm-hmm.
Oh, the conjugate.
Multiply by a conjugate. Keep your eyes on the one from before.
Okay.
Do you see how the denominator here and the denominator there are similar? It's 1 and then a trig function that is not squared. That's going to be your hint that we're going to multiply by the conjugate. So we are going to multiply by the conjugate here. So here we go. We have sine of theta over 1 plus cosine of theta, and we're going to multiply by the conjugate. What is the conjugate of this one? 1 minus cosine. So you just change the signs of the trig function itself. And again, the reason we're wanting to do this is because the denominator becomes the pattern difference of two squares. I'm still going to show all of the work, but if you know you can see the difference of two squares quicker and you can tell me that's the reason how you factored it faster, I'm fine with that. Or multiplied it faster, sorry. Which means, oh, let me write down a reason. This is multiply by the conjugate. So then we would have, again, I'm not going to cancel out this or distribute the sign yet, just in case it turns out nice. Over, I'm going to show how it may work. This is 1 minus cosine of theta plus cosine of theta minus cosine squared of theta. Just like last time, after we FOIL that denominator, we have positive cosine and negative cosine in my denominator, so it cancels out. And so I'm left with sine of theta, 1 minus cosine of theta, all divided by 1 minus cosine squared of theta. These steps have kind of followed the same thing. The reason we multiply by the conjugate is to get that difference of two squares, which also allows me to use the Pythagorean identity. What is 1 minus cosine? I wrote too big. Make your handwriting smaller if you're running out of space. This is sine of theta over 1 minus cosine of theta over what? Sine squared of theta. That's your Pythagorean. Bless you. Bless you. That's your Pythagorean identity. Just like last time. What happens? Sine cancels, sine cancels. So this becomes 1 minus cosine of theta over sine of theta. Now last time we got to finish here because that was the goal. But this time our goal is to have two separate terms, one being cosecant, one being cotangent. So question, can I split this apart now? I have a monomial. Am I allowed to split with monomials in the denominator? Bless you. Yes. Monomials is when you can split the denominator. So this becomes 1 over sine of theta minus cosine of theta sine of theta. Again, our very mathematical word, split. We are one step away. I have two pieces. What is the other definition for 1 over sine? Cosecant. What is the other definition for cosine over sine? And that was the goal we had. So we're going to do the reciprocal identity and the quotient identity to end at the same expression that we had on the left side, on the less complicated side.
Yeah.
Sorry that I wrote too big and ran out of a little bit of room. Look at all that space I wasted up there. Sorry.
Very unmathematician.
Do you start to kind of see how we're playing with these? It's the same rules as last time, just with a different goal than we had before. Our last one we're going to work with is this guy. This one's an obvious answer.
Yeah.
Which one's more complicated?
Okay.
we're gonna work with the left side and we're eventually gonna make it look like the right side. So our goal is to get this down to one term. Somehow, we're gonna have to get the plus sign to go away. That's gonna be an inside goal for us, is we gotta get that plus sign to go away because it's not in our goal. What do y'all wanna do first?
Tangent, cotangent.
What about those?
Change them to sine or cosine, cosine or sine.
Sure, all right, let's do that. So we have a cosine of theta in the very front. Tangent we can change to sine of theta over cosine of theta. That's the quotient identity. And cotangent we can change to cosine of theta over sine of theta. Times 2. Cool. What next? Let's distribute. Now I'm going to show some work on distributing because remember your work is your answer. So we'll distribute. This becomes sine of theta times cosine of theta over cosine of theta plus cosine squared of theta over sine of theta. That was my distribute step. Thoughts?
The cosines cancel.
The cosines cancel. Anything else?
Sines.
Ooh, remember, they can only cancel when you're multiplying. Those signs are being added. So can we cancel those? No. So that's actually it. Sorry, trick question. That means that we have sine of theta plus cosine squared of theta over sine of theta, and we got that because we did a cancel step. Yikes. Remember our goal? I said at some point we're going to have to combine these two things together.
Oh, yeah.
How do we combine these together?
Sine over sine. I was gonna say, can we do sine over sine?
Yes, we need to have them have a common denominator, so we're going to multiply them by sine on top and bottom. And by them, I mean the first term. So this first term we're going to change to be a denominator of sine of theta, which means I have to multiply the numerator by sine of theta. What is sine times sine?
Sine squared.
Sine squared. That second one already had the correct denominator, so no change. Give it a common denominator. Once they have, yes, sorry.
Why didn't we square it?
Remember right now, just the step before, sine had a denominator of 1
Oh, so you multiply both by, okay.
by sine, so then sine times sine is sine squared, yes. Once they have the same denominator, we can actually add them together. So we write it as one fraction with sine squared of theta plus cosine squared of theta on top. This is just adding fractions.
What is it? The sines?
I see two things that are squared. Where should we look on our formula chart when two things are squared?
Oh, it's 1.
Oh,
Yeah, we have that Pythagorean identity, yes? Sine squared of theta plus cosine squared of theta is equal to 1. That whole thing can be substituted for the number 1. That's your Pythagorean identity. We've gotten it down to one term. We've gotten it down to one trig function. Is it the right trig function?
Yes.
Because we're one step away. What is 1 over sine?
Cosine.
And that's what our identity wanted. This is my reciprocal identity, and now again, I've got it to match to that goal. Whatever the goal was, we had to match it up. So on your homework today, yes, there's only 8 problems. It took me 3 pieces of paper to do it. I wrote really big. You could probably fit it on one front and back. I was wasting space. I still want a reason for every step. So if you look over here, not super close so you see my work, but I have a step and a reason for each single question that I did. Okay, I expect to see the same thing on yours in nice, neat handwriting, which also means I probably should have put the quad paper out for you.
Well, this is how it's called. I don't want to.
So come grab some quad paper if you want it, or if you'd rather use a different piece of paper, that's fine. I'll put it out here in a second. Oh, will you wait till it comes back then? I forgot he was gone.